Subject DC machines. I refer from Falcon textbook. Unit number 1. Fundamentals of DC generators. I want to explain introduction. Introduction is very important to us. We know that electrical machines which converts electrical energy into mechanical energy is called motor. Similarly, which converts mechanical energy into electrical energy is called generator. So it is very important to us. Remember one thing, conversion through the electromagnetic induction motion is involved in the conversion which converts mechanical energy into electrical energy. EMF induced is said to be dynamically induced EMF. It is very important to us. One thing we have to remember, we know that if direct current is used to convert mechanical energy into electrical energy is called DC generator. Similarly, DC motor means nothing but if direct current is used for converting electrical energy into mechanical energy is called DC. Let's start next topic, classification of DC generators. Classification of DC generators, how many types it can be classified, now we are going to discuss. In case of DC generators, necessary magnetic field is produced by magnetic magnets, field magnets. Permanent magnets are used for very small capacity generators, and electromagnets are used for large capacity generators to produce magnetic flux. The actual classification of DC generators can be classified into two types. DC generators classified into two types: permanent magnets DC generators, electromagnets DC generators. Electromagnet DC generators can be classified into two types: separately excited DC generators, self-excited DC generators. Self-excited DC generators can be classified into three types: DC shunt generator, series generator, compound generator. Further, compound generator can be classified into two types: DC long shunt generator, DC short shunt generator. Just now we have completed classification of DC generators. Now EMF equation of DC generator, pi equals to flux per pole in Webers. Z equals to total number of armature conductors, open bracket, number of slots into conductors per slots. Okay, now N equals to speed. N represents, it is the speed of motor, speed of rotation of the conductor, units RPM. P equals to number of poles. A equals to number of parallel paths. In armature, Eg is equals to EMF induced in any parallel paths. Okay, therefore flux cut per conductor in one revolution. D pi equals to flux per pole into number of poles. D pi equals to flux into P Webers. flux per pole represents with pi. Number of revolutions per second equals to n by 60. Time taken for one revolution dt equals to 60 by n seconds. Okay, we do not have space. According to Faraday's laws of electromagnetic induction, rate of change of flux linkages d pi by dt equals to pi p by 60 by n, pi p n divided by 60. Therefore, average EMF generated per conductor equals to n d pi by dt. Therefore, EMF generated per conductor per second pi p n divided by 60 volts. In generator, if the total number of conductors is Z and conductors A EMF generated for Z number of conductors Eg equals pi Pn divided by 60 into Z volts. We know that we have two types of windings, lap winding and wave winding. Now consider a number of parallel paths in a generator. We have therefore generated EMF equals to Eg equals to pi Zn by 60 into P by A. P means nothing but number of poles, A means nothing but number of parallel paths. Here completed. EMF generated is completed. Next, in lap winding, number of parallel paths equals to number of poles. Okay, A is equals to P in lap winding. So what is formula? Generated EMF pi Zn by 60 into P by A equals to P అనుకున్నాం. So PP cancel, Z pi by volts. In wave winding, number of parallel paths equals to 2 means nothing but A equals to 2. So generated EMF formula వచ్చేసి pi Zn by 60 into P by A అంటే nothing but 2. So pi Zn P 60 into 2 120 volts. Now discuss induced EMF. When a magnetic flux linking a conductor or changes EMF induced in it means nothing but how EMF will be induced in the conductor. Induced EMF can be classified into two types: dynamical induced EMF and statical induced EMF. Dynamically induced EMF means nothing but dynamic means nothing but changes when conductor is moved in a stationary magnetic field in such way flux linking with the conductor. That's why EMF will be induced in the conductor. It is called dynamical induced EMF. Example, take a generator. Then statical induced EMF means nothing but statical, stationary or constant. Conductor is stationary, magnetic field is changing. EMF induced in this way. It is called as statical induced EMF. Transformer take. Suppose example, transformer. Transformer is a device which converts from which transfers energy from one place to another place with constant frequency 50 Hz. In transformer, we have step down transformer and step up transformer. Okay, here in transformer, conductor is stationary, magnetic field is changing. Magnetic field means nothing but in transformer primary winding, secondary winding. Primary winding is taken as input and secondary winding connected to output. And AC supply is given to transformer. If we give DC supply to transformer, the windings are to be burned. Statically induced EMF in this again classified into two types: self-induced EMF and mutual induced EMF. Magnetic field is dynamical induced EMF. Dynamic means nothing but changes. Okay, here EMF induced in the conductor due to its motion at uniform magnetic field means when conductor is moving in stationary magnetic field, it is said to be dynamical induced EMF. So here in the picture, figure A, figure B, figure C. Observe figure A. Conductor is moving parallel to the field. Figure B. Conductor is moving perpendicular to the field. Figure C. Conductor is moving at an angle with theta to field. Okay. Figure A. Conductor is moving parallel to the field. Then no EMF will be induced. No flux cuts conductor. Then no EMF will be induced. So E is equals to 0. Figure B. Conductor is moving perpendicular to the field. Then that conductor cuts flux. Then EMF will be induced. Induced EMF will be represented with E. E equals to beta flux density into length into velocity of the conductor. And figure C, conductor is moving with an angle theta. The two components V sin theta and V cos theta. V sin theta is perpendicular to the field and V cos theta is parallel to the field. So V cos theta is no cuts conductor. Flux does not cuts conductor. That's why no EMF will be induced. So EMF equals to flux density into length of the conductor into velocity of the conductor into sin theta. So here E equals to dynamical induced EMF in volts and L is length of conductor. Length units meters. Beta flux density Webers per meter square. V equals to velocity of the conductor meters per second square. Okay, according to Faraday's laws of electromagnetic induction, no, flux cuts by conductor represents with d pi. D pi equals to flux density into area swept. D pi equals to flux density means nothing but beta. Area swept means nothing but length into breadth ante small distance, certain distance. So L into dx Webers. Okay, next. We know that according to Faraday's laws of electromagnetic induction, d pi by dt induced EMF equals to n d pi by dt. Number of turns is equals to 1 and 1. Then B flux density into length into velocity divided by time. Okay, equation number 2. Finally, we gets induced EMF equals to flux density into length into velocity of the conductor into sin theta, certain angle. Before this topic, we discussed classification of DC generators. How many types of DC generators can be classified? Permanent magnets of DC generator and electromagnet of DC generator. Permanent magnet of DC generator, it is U-shaped permanent magnet, which is fixed to yoke. Yoke means nothing but which provides protection to the whole machine and which provides mechanical support to the poles. Armature is placed between poles, north pole and south pole, and load is connected across the armature. It is U-shaped permanent magnet, and these permanent magnets are used for small capacity generators. Now electromagnetic DC generator. Electromagnetic DC generator, it is used for large capacity generators, and it can be classified into again two types: separately excited DC generator and self-excited DC generator. We know that when electromagnet DC generators, this method is depends on excitation of field with armature. Okay, let us separately excited DC generator as shown in figure. Field is excited independent to armature, variable resistance, battery, field. These armature connected across the load. V is terminal voltage. when field current can be varied by varying the variable resistance which is connected to the battery. Okay, ఇక్కడ current can be varied by varying the resistance. Okay, it is separately excited DC generator means nothing but field and armature are connected separately. Next, self-excited DC generator means nothing but field winding is excited by current produced by generator itself. It is called self-excited DC generator means nothing but current produced by generator itself. It is called self-excited DC generator. Field poles must have residual magnetism due to present here in this self-excited DC generator. The field is connected across the armatures and connected in series with the armature. So here current produced by generator means nothing but armature. Field poles must have residual magnetism. Due to presence of residual magnetism, always some flux is present in the poles means poles purpose is to distribute the flux. So presence of residual magnetism, flux is present in poles, and field coils are interconnected with armature winding. Okay, self-excited DC generator can be classified into again three types: DC shunt generator, DC series generator, and DC compound generator. Let us discuss DC series generator. DC series generator means nothing but field windings are connected in series with armature. Field winding, this is field winding, this is armature, it is load. Load is connected across the armature, and this field winding is connected in series with armature. Due to connection in series, same current will be flows through armature and field resistance. Okay, armature voltage across the armature is equal to terminal voltage. When this field winding, this series resistance field winding is designed few tons means thick wire, large cross sectional area, then resistance is very low because of, take for example, it is this winding. Rubbers means nothing but winding. Assume like a winding, few number of tons. It is a thick. Cross sectional area is more. It is take as thin. Cross sectional area is very less. Okay. Here choose cross sectional area is more. That's why flow of electrons is more. Then current. Flow of electrons is nothing but current. So resistance is very less as compared to DC shunt generator. It is thick. It is thick wire. Okay. Next, voltage and current equations. Voltage and current equation DC series generator. IA equals to armature current in amperes. Ampere means units. ISC means nothing but series field current in amps. IL load current. RA armature resistance. Armature resistance to terminal voltage in volts. EC means generated EMF. EMF generated in volts. Units volts. Applying KVL to this loop. Actually, this science is depends upon, science means nothing but positive and negative. This depends on current direction. This loop clockwise direction. So here generated EMF. First of all, we take generated EMF. Generated EMF means nothing but back EMF, EG. Next, current direction of armature current. Ohm's law equals to V is equals to I into R. So armature current into resistance minus same direction with respect to loop. Got a negative. IA RA minus negative minus field winding resistance into series field current. ISC RSC equals to 0. Equals to 0, equation number 1. So terminal voltage direction also. Voltage is one side and this current into resistance one side. So okay, now we need generated EMF generator means something like back EMF. So EG, we want EG means generated EMF. Here see once EMF generated EMF కావాలి కాబట్టి సో LHS side ఉన్నది RHS side పట్టుకోవాలి. సో RHS side పోయినప్పుడు ఏమంటే నెగిటివ్ will becomes positive will becomes negative. So here EG sign వచ్చేసి positive కాబట్టి అటు పోతే ఏమైతే మైనస్. సో ఇవన్నీ మైనస్ V మైనస్ IA RA మైనస్ ISC RSC. ఓకే, మైనస్ కామన్ తీసేసి V ప్లస్ IA RA ISC RSC equals to minus cancel. We need EMF generated in volts. VG equals to V plus IA RA ISC RSC. In DC series generator armature current. DC series generator లో ఇక్కడ రెండు సిరీస్ ఉన్నాయి కాబట్టి కరెంట్ అనేది సేమ్ ఫ్లో ఇది రెండిట్లో కాబట్టి ఆర్మేచర్ కరెంట్ ఈక్వల్స్ టు లోడ్ కరెంట్ ఈక్వల్స్ టు సిరీస్ ఫీల్డ్ కరెంట్. హెన్స్ ఈజీ ఈక్వల్స్ టు V ప్లస్ IA RA ప్లస్ IA RSC. ఇక్కడ IA ఇండికేషన్ అంటే ISC అంటే సిరీస్ ఫీల్డ్ కరెంట్ దగ్గర IA ప్లేస్ చేసాం కాబట్టి ఇక్కడ IA అనేది కామన్ తీసుకున్నాం RA ప్లస్ RSC కన్సిడరింగ్ బ్రష్ కాంటాక్ట్స్. Now DC shunt generator. DC shunt generator means DC shunt generator. Discussed DC series generator. Here DC shunt generator field is connected across the armature. Means it is parallel connected across the armature. Okay, it is field winding. It is armature. It is load. In field winding is connected in parallel with armature. Here field winding is designed many turns. In series generator, field winding is designed few turns. Shunt generator designed with many turns. So cross sectional area is less. Cross sectional area is less. So thin wire. Thin wire means nothing but, suppose take example, it is pen, thin wire. Cross sectional area is less as compared to DC series generator. So resistance is high. Hence resistance of shunt field resistance is high. Voltage across the field is equal to is same as the terminal voltage. Terminal voltage of generator. Voltage and current equations of DC shunt generator. Let us discuss. RSH means it is shunt field resistance in ohms. ISH shunt field current in ohms. ISH equals to V by RSH means ohms of V is equals to I into R. I is equals to V by R. ISH is equals to V by RSH. Applying KCL to the point B. Because in parallel, if we connect the field parallel with armature, then current is divided. In parallel connection, current is divided. Applying, so current is divided means Kirchhoff's KCL means nothing but incoming current is equals to outgoing currents. Here point B, it is junction. So IA is incoming current, armature current is IL is load current, ISH is shunt field current. IA equals to armature current, incoming current equals to outgoing current, sum of IL plus ISH. IA equals to IL plus ISH. Next, applying KVL to the loop, we get same as it is compared to series generator. First, generated EMF. Loop is same direction. That's a negative armature current minus negative IA RA. Series shunt field resistance and shunt field current is neglected because of already we know ISH equal to V by RSH. That's why we did not take it. So minus V plus EG minus IA RA equals to 0. We need EMF generated. That's why E malad side we need. The EG equals to minus taken common V plus IA RA. Brush contact drop is given, then EG equals to V plus IA RA plus brush contact drop. DC compound generator. We discussed already DC series generator and DC compound generator. In this picture we are going to learn about DC compound generator. Actually DC compound generator has both series and shunt field windings. Again, this compound generator can be classified into two types: short shunt generator and long shunt generator. Okay, DC short compound generator, see figure, it consists of series and shunt field windings. So here the shunt resistance of shunt field winding is connected across the armature. That's why it requires only short length of wire for connecting shunt field winding across armature. It requires short length of wire. Okay, and voltage across the shunt field winding is sum. So now voltage and current equations of compound generator. Both the series and shunt field windings. It consists of series and shunt field windings. So in case of series, this series field resistance of shunt field winding equals to load current. Shunt field current equals to series field current equals to load current. ISC equals to IL load. So voltage across shunt field winding terminal is V equals to small v is voltage across the armature. Capital V is terminal voltage across the armature and series field resistance. So here shunt field winding, series field winding. Okay, here voltage across the shunt field resistance small v equals to terminal voltage plus series field resistance into current, series field current, ISC into RSC. Okay, V is equals to V plus IL RSC. Instead of ISC, we wrote IL because of series connection. Load resistance equals to series field resistance. Okay, in case of shunt field current, according to Ohm's law, V is equals to I into R. So I is equals to, we can be written as V by R. So here shunt field current ISH is equals to V by RSH. Applying KCL to the point B. Now we are going to apply KCL to the point B. Okay, KCL, incoming currents equals to outgoing currents. So here, one see from here, armature current it is shunt field current, it is series field current. So incoming current is armature current, outgoing current is series shunt field current and shunt field current. So sum of shunt field current equals to sum of shunt field current and series field current equals to armature current. Ia equals to IL plus ISH. Okay, applying KVL to the loop we get it. So same as it is loop, connecting loop. So here we already taken ISH means shunt field current. So it can be removed, and now loop, this loop generated EMF generated EMF EG, and loop is clockwise direction. This sign depends upon clockwise direction. So direction is like this. Same direction. ISC into first armature current and armature resistance IA RA, and armature series resistance and series current and series resistance equals to 0. Terminal voltage same direction with respect to clockwise direction. That's why we are taking negative. Okay, now we want only EG generated EMF. Generated EMF will goes to RHS side. So as it is right, V minus IA RA minus ISC RAC equals to minus EG. So we need to remove this minus. We are going to cancel this minus. So minus take common to left side. Minus take common. So V plus IA RA plus ISC RAC. Okay. Next equals to minus EMF generated, back EMF. Minus cancel. So we get already EG equals to V plus IA RA plus ISC RAC. Okay. Next, in case of series, the load current and series field currents both are equal. That's why IA RA ISC RAC take common. DC long shunt compound generator. Resistance of shunt field winding connected across the both armature and series field resistance. This field resistance is connected across the series field resistance and armature. So here voltage appears across the shunt field resistance is equal to terminal voltage of the generator. Okay, field windings are connected across. Okay, next it requires a long length of wire for connecting the shunt field resistance. To both series field resistance and armature. So it requires a long length of wire. From A to B. Okay. Next, voltage and current equations of the long shunt compound generator. In case of series, ISC equals to IA means nothing but series field current equals to armature current. Okay, shunt field current ISH equal to V by RSH as it is. Okay, applying KCL at point B. Armature current equals to incoming currents equals to outgoing currents in KCL according to Kirchhoff current law. So IA equals to IL plus ISH. Applying KVL to the loop we get. So in this shunt field current already taken. So we don't want shunt field current. So applying this loop KVL to this loop. So current direction is with respect to loop. That's why same as it is. Terminal voltage minus V same because of direction is same. Next plus back EMF generated EMF minus negative, and armature current and armature resistance. Series field current and series field resistance ISC into RC equals to 0. Okay, minus this generated EMF will goes to RHS side minus V minus IA RA as it is minus ISC RC equals to minus. Okay, minus cancel all to minus common issue V plus IA RA plus ISC RC equals to minus GG. Minus cancel EG equals to V plus IA RA plus IA RAC. In series condition, low armature current equals to series field current. That's why IA take common RA plus RAC. Series field current equal to armature current. Okay, EG equals to V. EG means nothing but back EMF or EMF generated equals to V plus IA common RA plus RAC. BCD means nothing but ratio contact drops. Okay. Remember one thing, in series additional resistance can be added to armature resistance, but shunt only. Okay, successfully completed DC series generator, DC shunt generator and compound generator. Means nothing but these are the self-excited generator, can be classified into 3 types: series, shunt, compound. We discussed this both pre. Losses in DC generator. Total losses in DC generators can be classified as follows. Total losses can be classified into three: copper losses, magnetic losses or iron losses or core losses. Okay, another one is mechanical losses. Okay, copper losses again can be classified into 3 types: armature copper losses, shunt field copper losses, series field copper losses. And iron losses can be classified into again 2 types: hysteresis losses and eddy current losses. Okay, next mechanical losses can be classified into again 2 types: frictional losses and windage losses. Now we discuss each and every one. Copper losses can be classified into 3 types: armature copper losses, shunt field copper losses, series field copper losses. Okay, armature copper losses it is denoted by IA square into RA. This is the copper losses, armature copper losses. These losses is about 30 to 40% of full load. Okay, next shunt field copper losses. ఇట్ ఈస్ యాక్చువల్ కాపర్ లాసెస్ ఫార్ములా వచ్చేసి IA square RA. సో స్ట్రెంత్ కాబట్టి ISH square into RSH ఆల్సో కాల్డ్ as కాన్స్టెంట్ లాసెస్. స్ట్రెంత్ ఫీల్డ్ కాపర్ లాసెస్ ఆల్సో కాల్డ్ as కాన్స్టెంట్ లాసెస్. సిరీస్ ఫీల్డ్ కాపర్ లాసెస్ యాక్చువల్ కాపర్ లాసెస్ ఫార్ములా వచ్చేసి I square R. సో హియర్ ISC square series field current and series field resistance. Okay, this losses is about to 20 to 30% of full load losses. Series field వచ్చేసి 20 to 30% of full load losses and armature copper losses వచ్చేసి 30 to 40% of full load losses. Next, iron losses or core losses or magnetic losses. These magnetic losses we know very well. These losses are practically constant for DC shunt and DC compound generator. So field current is practically constant in them. Because of losses are practically constant for DC shunt and DC compound generator, then field current is also practically constant. Due to rotation of iron core of the armature in the magnetic flux of the field poles means rotation of iron core of the armature ante rotation of armature in magnetic flux means which is present in field poles. These some losses are taking place continuously in the core is known as iron losses or core losses. Iron losses or core losses means nothing but rotation of armature core in magnetic flux. There are some losses. అంటే ఒక ఆర్మేచర్ కోర్ అనేది మ్యాగ్నెటిక్ ఫ్లక్స్లో రొటేట్ అయినప్పుడు అక్కడ ఏమైందంటే సమ్ లాసెస్ టేకింగ్ ప్లేస్ కంటిన్యూస్లీ ఇన్ ద కోర్. ఆ కోర్లో సమ్ లాసెస్ జరుగుతాయి. ఆ లాసెస్ ఏమంటాం మ్యాగ్నెటిక్ లాసెస్. ఓకే, ఐరన్ లాసెస్ ఆర్ కెన్ బి క్లాసిఫైడ్ అగైన్ టూ టైప్స్, హిస్టెరిసిస్ లాసెస్ అండ్ ఎడీ కరెంట్ లాసెస్. ఇక్కడ హిస్టెరిసిస్ లాసెస్ ఎలా వస్తాయి, ఎడీ కరెంట్ లాసెస్ ఎలా వస్తాయి అంటే ఇక్కడ హిస్టెరిసిస్ లాసెస్ అండ్ ఎడీ కరెంట్ లాసెస్ దిస్ లాసెస్ ఈజ్ అప్ టు 20 to 30% ఆఫ్ ఫుల్ లాసెస్ యాజ్ ఈక్వల్ టు సిరీస్ ఫీల్డ్ కాపర్ లాసెస్. ఓకే, ఇక్కడ హిస్టెరిసిస్ లాసెస్ అని ఎలా వస్తాయంటే ఆర్మేచర్ అనేది ఒక రొటేటింగ్ పార్ట్. ఒక మిషన్లో ఆర్మేచర్ ఇది ఒక రొటేటింగ్ పార్ట్. సో అక్కడ ఆర్మేచర్ అనేది ఫ్లక్స్ని కట్ చేస్తాను. ఆర్మేచర్ కట్స్ ఫ్లక్స్. దెన్ ఆ ఫ్లక్స్ అనేది రివర్స్ అంటే నార్త్ పోల్ టు సౌత్ పోల్ ఫ్లక్స్ అనేది ఫ్లో అయ్యేటప్పుడు ఇక్కడ మన జనరేటర్లో రివర్సల్ ఫ్లక్స్ టేక్స్ ప్లేస్ ఇన్ ఆర్మేచర్. దెన్ హిస్టెరిసిస్ లాసెస్ ప్రొడ్యూస్డ్. Reverse flux takes place in the armature core. Hence hysteresis losses are produced. So we need to minimize the hysteresis losses. So actually this iron losses is armature core is made up of silicon steel, high permeability silicon steel for the purpose of to minimize the hysteresis losses. Okay, understood. Next, eddy current losses. When armature cuts magnetic flux, armature core cuts magnetic flux, EMF will be induced. According to Faraday's law, when your conductor cuts magnetic flux, EMF will be induced. There is eddy current losses are produced. Okay, next, mechanical losses. Mechanical losses means nothing but frictional losses and windage losses. Actually, frictional losses occurred at the place of armature core is rotating parts దగ్గర frictional losses అనేది occur అవుతాయి. So mechanical losses can be classified into frictional losses and windage losses అని అనుకున్నాం. So frictional losses occurs at bearings and commutator. Okay, next, air friction. Windage losses is occurred in rotating armature. Okay, again we are going to discuss this eddy current losses and hysteresis losses. So here hysteresis losses can be represented by hysteresis losses can be represented by WH equals to eta flux density. It is flux density, maximum flux density power 1.6 volume in such a watts. Okay, V means nothing but volume. V is volume of the core. Unit such as meter cube. Volume and length into breadth into height also unit such as meter cube. Next, and F also. F means F equals to frequency of the magnetic reversals. Frequency of magnetic reversal. Next, it is eta. Efficiency అనుకుంటాం మనం, బట్ ఇక్కడ వచ్చేసి eta Steinmetz hysteresis coefficient. Okay, see here, hysteresis losses represented with WHO eta maximum flux density power 1.6 volume frequency. Okay, ఇక్కడ వచ్చేసి this losses is depends on volume and grade of iron, maximum value of flux density. Okay, ఇక్కడ వచ్చేసి losses is depends upon flux density and volume. volume and frequency of magnetic reversals. Okay, here hysteresis losses you can write as directly proportional to frequency. Hysteresis loss is directly proportional to frequency. Okay, next let us discuss eddy current losses. ఇది వచ్చేసి hysteresis loss అయిపోయింది. Eddy current losses. Eddy current losses discuss చేద్దామా. Eddy current losses can be represented by WE. Okay, next formula WE equals to K maximum oxygenicity square frequency square T square volume square watts. Okay, K equals to nothing but is constant, depends on the electrical resistance of the core. Okay, K is nothing but K equals to constant, K is constant, depends on electrical resistance of the core. Okay, beta is maximum flux density, V equals to volume in meters, meter cube. F is frequency of magnetic reversals. Always these eddy current loss is directly proportional to frequency square of frequency. Okay, due to presence of eddy current losses, efficiency of generator decreases. Due to presence of eddy current losses, efficiency of generator decreases and temperature increases. ఇప్పుడు ఇక్కడ presence of eddy current losses ఇక్కడ మనకి ఏమవుతుందంటే efficiency is decreased and temperature is increased. Efficiency decreased, temperature increased. Okay, understood? Successfully we completed losses in DC generator. Next I want to do problems in next video. The overall fundamentals of DC generator I covered. What topics are present in fundamentals of DC generator? ఒక DMF equation నేర్చుకున్నాం. నెక్స్ట్ క్లాసిఫికేషన్ ఆఫ్ DC generators నేర్చుకున్నాం. నెక్స్ట్ లాసెస్ ఇన్ DC generators నేర్చుకున్నాం. నెక్స్ట్ ఇంకొక టాపిక్ ఏం వదిలేసిన అంటే కన్స్ట్రక్షన్ ఆఫ్ DC generator, పార్ట్స్ ఆఫ్ DC generator, కన్స్ట్రక్షన్ అండ్ పార్ట్స్ ఆఫ్ DC generator. ఒకటి అది పెద్ద టాపిక్ కాబట్టి అదొకటి సెపరేట్ ఇంకొక వీడియో తీయాలని అనుకుంటున్నాను. సో హెన్స్ కంప్లీటెడ్ హియర్. Successfully completed, but again we have stray losses. Magnetic and mechanical losses is known as stray losses. Constant losses means nothing but constant losses is represents with WC equals to shunt copper losses and stray losses. Stray losses means magnetic and mechanical losses. Okay, shunt copper losses plus magnetic plus mechanical losses. Okay, variable losses means nothing but which is also called armature copper losses. Okay, total losses equals to variable losses plus constant losses. Variable losses and IA square RA, and armature copper losses plus constant losses. Armature copper losses is nothing but variable losses. Constant losses are okay. Hence this lesson is completed. Fundamentals of DC generator we learned something. At least 1% knowledge మీరు గెయిన్ చేసుకుంటారు ఈ టాపిక్స్ అన్ని at least 1%.